Good afternoon. We are going to be doing notes for section 6.1. This is probably the largest section of notes in the chapter because it goes over all of the vocabulary that we're going to be using for the rest of chapter 6. You might want a couple different colors of ink. But there are no constructions on this particular segment. Now you'll also want your ruler. So if you don't have those, go ahead and pause the video, get your tools, and start up again. Okay, Roman number 1, Polygon Vocabulary. The definition of a polygon is that each segment intersects with exactly 2 other segments at their endpoints. The second part of the definition, no 2 segments with a common endpoint are collinear. So if we look at these examples and to decide which are going to be polygons and which ones are not, the first part, each segment intersects with exactly 2 other segments at their endpoints. That means that this segment here intersects with the endpoints of the left side and the right side. In something like this one, you have a segment that's intersecting with multiple pieces at the same time. So while this one is a polygon, this one is not a polygon. No 2 segments with a common endpoint are collinear. What does that mean? Well, it means that on a shape, you can only have endpoints here and here on either end. You can't have one in the middle. And that's on this one here. If you had an endpoint here so that it's in between the other 2 and it makes a line, then it's not a polygon. So it has to be only at the endpoints of the figure. The last part about the definition is there can be no curves. So this shape right here is not a polygon because it has curved sides. The second reason that this shape here is not a polygon, so it's not a polygon because it has 2 segments but share an endpoint and are collinear. It's also not a polygon because this endpoint is not touching another endpoint. So you could think of this as it's an open figure. It doesn't close, and that's why it is not a polygon. All right, vocabulary number 2, interior angles. Interior angles are inside the figure at a vertex. And a vertex, of course, is where 2 sides meet up. Exterior angles are when one side is extended. So an interior angle of a triangle, if we draw ourselves a triangle, it has 1, 2, 3 interior angles. If I extend this bottom side out, this angle here is the exterior angle, which is created when one side is extended out. Okay, vocabulary term number 4, a convex polygon means that no sides of the polygon are on the interior of the figure. So examples 1 and 2 are both convex. No sides are on the interior. It's kind of easier to determine non-convex or concave than it is convex. Concave, if you want to think of it as a little cave, it means that one of the vertices has caved inside the figure. Another way to look at it is I can take a straight edge and I can connect 2 vertices while skipping one. On these figures, if I connect 2 vertices, I'm always going to be sliding on the outside of the figure. I never punch into the figure, which is why these are convex, and these are concave. In your book, they like to go to non-convex. We're not actually going to use that term. We're going to use concave because that's the more specific term. Okay, number 5, diagonals is a segment joining non-consecutive vertices. Consecutive means in a row. Non-consecutive obviously means not in a row. So if I take a ruler here, this shape is a regular pentagon. So go ahead and write that label on it, regular pentagon. Pentagon because it has 5 sides, regular because all the sides and all the angles are the same. So if I want to draw the diagonals, I have to connect each vertex with the vertices that are not next to it. So this one needs to be connected from there and there. When I move on to this one, again, I'm not going to connect to the one that's next to it. It's only going to be ones across the figure. Connect that one. On this vertex, it's already connected across. Here's the second one. So on this figure, there are actually 5 diagonals, if you count them up. This figure is also a pentagon. So let's label it pentagon. It is not a regular pentagon, though, because the sides are not the same lengths and the angles are not the same measure. It's just a plain old pentagon, a 5-sided figure. So if I draw the diagonals to this figure, again, from one vertex to a non-consecutive vertex, so there are 2 I can connect that one with. There are 2 I can connect the second one with. The third one is already connected to one, but I need to connect it to the other. And the others are taken care of. So you'll notice that these both made stars, and the stars are made up of 5 diagonals. So evidently, it doesn't matter if a pentagon is regular or not regular. If it has 5 sides, it's going to have 5 diagonals. And again, the word pentagon means 5 sides. Okay, flip the page. We are going to be learning how to name polygons by the number of sides. I think you know some of these already. A 3-sided polygon is a triangle. 4-sided is a quadrilateral. 5-sided is a pentagon. 6-sided is a hexagon. Now here's the ones that most people don't know as well. A 7-sided figure is a heptagon. H-E-P, heptagon. An 8-sided figure is an octagon. Most of you know that one. A 9-sided figure is a nonagon. Nonagon. A 10-sided figure is a decagon. We're going to skip 11 for right now. A 12-sided figure is a dodecagon. And there are other names, but those are the ones that you're expected to know. For any other numbers of sides, we just state the number of sides n with a hyphen and gone. So the one that we skipped, where n equals 11 sides, we're going to call that an 11gon. So then 13 gone, 14 gone, 15 gone, 16 gone, and so on. Those are ones you do not need to learn specific names for. You can use this generic labeling system. All right, vocabulary number 7, a regular polygon. A regular polygon is equilateral, equal side lengths, and equiangular, equal angle measures. All right, so let's do some labeling. We're going to practice. Describe the polygon as equilateral, equiangular, or regular. And remember that regular means it's both. Describe it as concave or convex, and name it by the number of sides. Okay, so looking at this, all the sides are the same, all the angles are the same. So this is a regular figure. There is no line that I can draw that will punch into the figure, so it is a convex figure. And it has 5 sides, so it is a pentagon. Notice the order of the terms: regular, convex, pentagon. The last one is the name by sides. Okay, let's look at number 2. Number 2, first of all, we're looking for equilateral or equiangular. Well, you can tell it's got long sides and short sides, so it's not equilateral. But the angles in all 6 places are actually the same. So number 2 is equiangular. I cannot draw any line that will punch into the figure. They all stay on the outside, so it is convex. And there are 6 sides, so this is a hexagon, an equiangular convex hexagon. All right, number 3. So you can tell that the sides on this are not equal. You got some long ones in here, so it's not equilateral. The angles go from obtuse to acute, so it is not equiangular. So we're not, and it's definitely not regular, because regular means both equilateral and equiangular. If I draw a line on this side, it punches into the figure. So this figure is concave, or it has a little cave in it. And if we count the sides, there are 7 sides. It is a heptagon. So a concave heptagon. And the last one, number 4, obviously it has long sides and short sides, so it is not equilateral, but all 4 angles are 90. So we can say this is equiangular. Any side that I extend will not punch into the figure, so it is convex. And it has 4 sides, so it is a quadrilateral. An equiangular convex quadrilateral. All right, there's our descriptions. All right, let's get into some of the theorems. First one, the polygon interior angle sum theorem. Here we go. It says the sum of the measures of the angles of any convex polygon with n number of sides, which just means a generic number of sides, is, so the sum of the interior angles, the number of sides n minus 2, and then you multiply it by 180 degrees. This formula actually works with both regular and irregular polygons. As long as it's a polygon, you can calculate the sum of all the interior measures. Now notice that it's the sum of all of them. This formula does not give you one particular angle. So let's practice this. And these are just like the problems on your homework. Okay, example 1, the sum of the interior angles of a triangle. Okay, so because this is a triangle, n equals 3 sides. So using our formula, 3 is our n, minus 2 times 180 degrees will give us the sum. Well, 3 minus 2 is 1, and 1 times 180 degrees is 180 degrees. This makes perfect sense because the sum of the angles of a triangle are always 180. That would be the triangle sum theorem. So it agrees. Okay, example 2. The sum of the interior angles of a square. Okay, a square has 4 sides. So n equals 4. So 4, there's our n, minus 2 times 180 degrees. Well, 4 minus 2 is 2. 2 times 180 degrees is 360 degrees. Which makes sense because a square is all 90-degree angles, so 90, 90, 90, 90 will be 360. Okay, this is a corollary to 6-1. Corollary means it's highly related. This is the measure of, and we're going to say, it says an interior angle. By an, we mean 1 interior angle of a regular n-gon. So the Polygon angle sum theorem is good for regular and non-regular, but the corollary only works for regular figures, equal sides, equal angles. So the formula for the measure of one of those identical angles is n minus 2 times 180 degrees divided by n number of sides. All right, let's practice this. Find the measure of one angle of a regular nonagon. Okay, so a nonagon has 9 sides, so n equals 9. We're looking for one angle. So here we go. N minus 2, so 9 minus 2 times 180 degrees divided by 9. There's our setup. All right, 9 minus 2 is 7. So I have 7 times 180 degrees on the top divided by 9. 9 goes into 180 20 times. 20 times 7 is 140 degrees. That is the measure of one angle of a regular nonagon. All right, number 2, find the measure of one angle of a regular pentagon. Okay, I want you to pause the video and work this problem out for yourself and then turn the video back on. Go ahead and do that. Okay, we've turned our video back on. A regular pentagon has 5 sides, so n equals 5. So we're going to go 5 minus 2 times 180 degrees divided by n, which is 5. Well, 5 minus 2 is 3. So 3 times 180 degrees over 5. And there's a really easy way to reduce this. 180 is 5 times 36. And then we have a 5 on the bottom, so we can divide the 5s out, and we get 108 degrees for one angle of a regular pentagon. I hope you got that one right. Okay, C, polygon exterior angle sum theorem. Probably the easiest one we learn because it says the sum of the measures of the exterior angles of, here's the great part, any convex polygon, one angle at each vertex is 360 degrees. And this is always true. It's always 360 degrees. And it works with both regular and irregular polygons. All right, so with our example here, we're going to prove that this theorem is true. We have here a 1, 2, 3, 4, 5. This is a pentagon. It's not regular. And we have all the exterior angles. Notice that the exterior angles kind of look like spokes of a pinwheel. You know, the thing with the pin in the middle and then it spins. When you draw your exterior angles, they should always go in the same direction, either all counterclockwise like this one or clockwise, but they have to go the same direction. Well, if I take this and add it up, 102 plus 81 plus 63 plus 90 plus 24, we want to know, is it really 360 degrees? All right, let's chunk this. 102 plus 81 is 183. 63 plus 90 is 153. 153 plus 24 is 177. And 183 plus 177 equals 360 degrees. So yes, the theorem is true. All the exterior angles add up to 360 exactly. Flip the page. All right, we're going to do some examples that are just like the homework assignment. So this will give you a little pre-practice before you start. Part A says find the measure of one interior angle. So the first thing you should do is write your formula down from your theorem. N minus 2 times 180 degrees divided by n. So we're going to do this for a regular hexagon. Okay, hexagon has 6 sides, so n equals 6. So we're going to substitute a 6 in. So 6 minus 2 times 180 degrees divided by 6. 6 minus 2 is 4 times 180 degrees over 6. 6 goes into 180 30 times, and we get 120 degrees for one angle. Okay, again, I want you to try number 2 on your own. Pause the video and turn it back on when you're done to check your work. Go ahead and do that. All right, now we're back. A regular octagon. N equals 8 sides for an octagon. Substituting that into the formula, we get 8 minus 2 times 180 degrees all over 8. And then we simplify. 8 minus 2 is 6 times 180 all over 8. And you can reduce this however you want. I'm just going to factor it. 6 is 2 times 3. 180 is 18 times 10. So 233 for the 18. 2 times 5 for the 10. All over 8, which is 222. You can divide out your 2's, and you're left with 3335, so 27 times 5, which is 135 degrees. I hope you got that one right. Okay, part B of the practice. Find the sum of the measures of the interior angle. So this time we want the sum of all of them. So first thing you should do is write your formula, n minus 2 times 180 degrees. And this formula, it can be regular or not regular. It still works. So number 1, the sum of the measures of the interior angles of a polygon with 7 sides. So n equals 7. Substitute that into the formula. 7 minus 2 times 180, which is 5. Times 180, and if you multiply that out, it's 900 degrees. Notice that the sum numbers are definitely larger. There are more angles being added up. Okay, for a 17-gon, n equals 17. Substitute it into the formula. 17 minus 2 times 180. 17 minus 2 is 15. Times 180, and yes, I would definitely have to multiply that out. It ends up being 2,700 degrees. Okay, practice C. Find the sum of the measures of the exterior angles. This should be super easy because our theorem says the exterior angles always add up to 360. So it doesn't matter if it's a pentagon, it's 360 degrees. If it's a nonagon, 9-sided figure, 360 degrees. So those ones don't require any work at all because the theorem tells you it's always 360. All right, D, draw all exterior angles. Okay, you can pick a direction. I typically pick counterclockwise. So you're going to take each side and extend it outward, going in the same direction. These are all the exterior angles. And again, it should look like a pinwheel. The exterior angles should never go towards each other. There we are. Sometimes people get confused about which is the exterior angle and which is not. It's pretty easy. If you, let's pick this top vertex to concentrate on. This angle here is 180 degrees. That's not the exterior angle. The exterior angle will be less than that. It will be the small angle. That is actually the exterior angle. So when in doubt, figure out which one's 180 and pick the other one. And as a last example on your homework, one of these comes up. They give you a figure like this one, which, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 sides. Let's do a separate example. I don't want to get that one confused. So let's say that you have a 9-sided figure. Actually, 900. Let's make it a 7-sided figure. That's better. A 7-sided figure. And we know that our 7-sided figure has interior angles whose sum is 900 degrees. That's the sum of the interior angles. Let's say that they didn't know it was 7-sided. They just tell you it's n-sided, and they want you to find the number of sides. So all they've given you is the sum of the sides, which is 900. So the formula for the sum of the interior angles is n minus 2 times 180. That equals 900. And that would be your equation. And then you would just put dot, dot, dot. You would solve for n. So if they give you the sum of the angles, you can always solve backwards and figure out how many sides there were in the original figure. And I'll let you do that one for practice later. This is actually the end of the notes, so thank you for your attention. Have a great afternoon.